So we'll be deriving the Navier-Stokes equation starting from the force balance equation. So here we have a control mass tau bounded by the surface S. Here is a small cross section on the surface S where n is the normal and u is the corresponding velocity vector at this point. Now for this control surface we can write d dt of theta times d tau integral over tau, where theta is any parameter that we are considering. For instance, it can be the density rho. In that case, it would indeed, this term would indicate the rate of change of mass inside the control volume, and that will be 0. And we can next expand this term using the Leibniz theorem, and we will get a expansion of this form, where this first term will represent the local rate of change of the parameter that we are considering, theta, which can be density or momentum or anything. And the second term is analogous to the movement of the boundary S. Next, we apply the divergence theorem on this second term and get an expression of this following form. And next, we expand this second term and rewrite this expression in the following form, that is dou theta by dou t plus u times the gradient of theta plus theta times the divergence of u whole times d tau. Now these first two terms, they can be clubbed together as the material derivative of the parameter theta, and the second term will remain as it is, and we can rewrite these entire expression in this following form, that is integral over tau of material derivative of theta plus theta times divergence of u whole into d tau. Next, the parameter theta can always be represented in some sort of a function of rho. Any parameter that we consider, for instance the mass, can be represented in terms of the density. So rewriting theta as rho theta and plugging in the values in the original expression that we had just derived, we get d dt of integral of rho theta times d tau equals to material derivative of rho theta plus rho theta times divergence of u times d tau. And expanding this material derivative, we get this expression, that is rho times material derivative of theta plus theta times material derivative of rho plus rho theta times divergence of u times d tau. Now these two terms is equivalent to the continuity equation. They represent the continuity equation, and hence this can be equated to 0, and we are finally left out with this term. So the final expression that we get is of this form, and we can get this if we replace theta by u. This is the final expression that we'll get, and this is equivalent to the Newton's second law, rate of change of momentum equals the summation of all the forces, because we can see that this left hand term on this equation is representing the rate of change of momentum of the fluid particles, and the term on the right hand side shows the summation of all the forces such as body forces and the surface forces that are acting in the system. Next, taking into consideration just the I component of velocity, like instead of u, we'll be replacing it with ui. We'll get this following expression where Fi represents the volume forces, the body forces in the ui direction, in the I direction, and these are the summation of all the surface forces that are present. Using the expression that we have just derived here, we can rewrite this term as rho times material derivative of ui times d tau. This equals integral over tau rho times Fi times d tau plus, applying a divergence theorem on this second term, we can rewrite this as integral over tau dou sigma ij by dou xj times d tau. Since we are integrating over an arbitrary control, since we are integrating over an arbitrary region of fluid mass, we can withdraw these integral sign and rewrite this expression in the following form, that is rho times material derivative of ui by dt equals to rho times fi plus dou sigma ij by dou xj. And this represents the familiar Navier-Stokes equation without the viscous mu term. So this is the equation of motion, the Cauchy tensor or the Navier-Stokes equation. Now we move on to computing sigma ij by dou of sigma ij by dou of xj. We need to compute this term now in order to find out the final Navier-Stokes equation form. Now we can say sigma ij equals to minus p times delta ij. Now this is for a fluid element at rest, and sigma ij equals to minus p times dou ij plus dij for a moving element. Now this, as we all know, represents the isotropic term, and this represents the deviatoric term. Now we first derive the stretch tensor from the Cauchy construction. For this following configuration, where del A1, del A2, del A3 represent the corresponding surface areas on the sides of the tetrahedron that we have, and minus A, minus B, minus C represent the respective normal to these surfaces in each direction, we can write the summation of forces as sigma of minus A times del A1 plus sigma of minus B times del A2 plus sigma of minus C times del A3 plus, for this topmost surface that we have, considering its area to be del A and the normal perpendicular to this surface to be n, plus sigma of n times del A, we get sigma times n times del A minus sigma of A times del A1 plus sigma of B times del A2 plus sigma of C times del A3. This can be represented in this following form. And next, considering the ith component of the summation of forces sigma, we get sigma I times n minus sigma in the I direction times A times AI nj plus sigma ith component B times Bj times Nj plus sigma ith component C Cj Nj times dou A delta A equals to 0. So we have ith component Aj Nj plus Bj Nj plus Cj Nj times delta A equals to 0. So this can be simplified as Na equals to the volume force Fb plus the surface force Fs. Writing these in the order of x, this can be represented as dou V, that is in the order of del x cube, This too will be represented in terms of delta volume, again in order of del x cube, and this is delta A, so in order of del x square. Now if we take delta x tending to 0 as limit, then this, from this we can get the surface force Fs will be 0, because these two terms being in the order of x cube will cancel out. They'll almost be tending to 0, both these terms, and will be left out with Fs. So Fs equals to 0. Thus the surface forces should balance out. So we are left out with this: sigma I n equals to, as we are continuing with the ith component notation, Aj times sigma in the I direction, Bj the ith direction, C times Cj times normal in the n direction. Finally we get n equals to sigma ij times nj, where nj is the direction of the normal and sigma ij is the direction of force per unit area. So this is the Cauchy, the stress tensor derivation from the Cauchy construction. We prove that the stress tensor is symmetric. Considering an arbitrary system, this being the coordinates of the system, at a distance r, let force dF be acting on this and let this point be P. Then we can write the moment dm equals to r cross dF, or F equals to surface integral of r cross dF, which equals to surface integral of epsilon ijk times rj times sigma kl times nl times dA. Now this term together represents the elemental force dF. Next, using the divergence theorem, this above expression can be rewritten as volume integral of epsilon ijk dou by dou re times rj times sigma kl times dV. Next we apply the chain rule to this term and we get, applying chain rule, we get integral of epsilon ijk times dou rj by dou rl, this is rl, times sigma kl plus rj times dou sigma kl by dou rl times dV. Now this term is nothing but dou jl, the Kronecker delta. This equals to epsilon ijk times sigma kj plus rj times dou sigma kl by dou rl whole times dV. Now if we compare both these two terms, we see that the moment due to the volume forces will be negligible, as they'll decrease in the order of del x cube, so they'll decay faster compared to this first term. So as del x tends to 0, what we are left out with is m equals to the volume integral of epsilon ijk times sigma kj times dV. Therefore, epsilon ijk times sigma kj equals to 0, or sigma kj equals to sigma jk. Hence we have proved that the stress tensor is symmetric. Next we show that the stress tensor is isotropic for a fluid at rest. For a fluid element at rest, we can write sigma ij equals to minus p times del ij. And now since we know that the stress and tensor is symmetric, we can write the stress tensor sigma ij in terms of the principal axis. So we have written the tensor in the form of diagonal terms, and now this can be decomposed into two parts. First being this 1/3 of sigma ii 0 0 1/3 of sigma ii 0 0 0, and the same term here. This plus sigma 1 1 dash minus 1/3 of sigma ii 0 0 0 sigma 2 2 dash minus this term 0 sigma 3 3 dash minus 1/3 of sigma ii. Now as is evident, this first matrix is somewhat similar to that of an identity matrix multiplied by a scalar 1/3 of sigma ii. So we can infer that this matrix won't change its value depending on whether or not we are rotating the axis. So this value will always remain the same. So even if we rotate the axis, this won't make any difference. So we call this matrix as the isotropic matrix, and this as the deviatoric matrix. These are the corresponding stress tensor representations for the isotropic and the deviatoric part. So these represent the forces that act on a fluid element in case of the isotropic as well as the deviatoric cases. Now from the deviatoric stress matrix, we can observe that the trace of the matrix is 0, which means that the forces that will act on the fluid element is in equal and opposite direction. That is, it will act in such a way that they all cancel up, and the net force that acts on the fluid element under the deviatoric stress condition is 0. So now if we compare both these fluid elements under the corresponding stress forces, we can see that the fluid element under deviatoric stress will undergo some sort of deformation, while there will be no deformation for the fluid element under the isotropic stress case. So from these we can infer that for a fluid element at rest, the stress tensor is isotropic. So we have derived the stress tensor from the Cauchy construction. We have proved that the stress tensor is symmetric, and also we have proved that the stress tensor is isotropic for a fluid at rest. And using all these conditions, we have derived the equation of motion for this particular control volume, which is the basis of the Newton's second law of motion, and we have modified it to arrive at this final Cauchy-Navier equation of motion. Next, we obtain an expression for the stress tensor in terms of the velocity gradient by assuming that the fluid is isotropic. So we know for a fluid element at rest, the stress tensor sigma ij equals to minus p times delta ij. This is for fluid element at rest. And we have sigma ij equals to minus p times delta ij plus d times ij, where this is the isotropic term as we have just derived earlier, and this is the deviatoric term. This is for fluid element in motion. Next we try to determine dij. Now we can postulate that dij is related to dou uk by dou xl, where del uk by del xl is related to the relative motion of points, which in turn will generate stress in the fluid. Let's suppose these are my relative fluid particles A, B, C, D. So relative movement between these fluid particles will result in some sort of stress in this area. Now these two tensors can be related in this form: dij equals to A ijkl fourth order del uk by del xl, where this is a 3 cross 3 matrix, del ij is 3 cross 3, and aijkl is 3 cross 3 cross 3 cross 3. So this is a relation between these two tensors that we have. Now aijkl is determined by assuming that the fluid is statistically isentropic, which means that the deviatoric stress generated in an element of the fluid by a velocity gradient is independent of the orientation of the element. Now this applies to all gases and simple liquids which have an isotropic structure. But this assumption doesn't hold for complex fluid elements such as chain of polymers. And here we are already assuming that the fluid is isotropic, so we can go ahead with this assumption that we have. So aijkl is a fourth order isotropic tensor. Now I can write aijkl as combination of all possible second order isotropic tensors del ij, that is aijkl equals to, let's say, mu double prime times delta ij times delta kl plus mu prime, another combination is delta il times delta jk plus mu times delta ik delta jl. These are all the possible combinations of the second order tensor delta. Now we had already proved earlier that sigma ij is symmetric. We had proved this earlier that the stress tensor is symmetric. So sigma ij is symmetric. So once we remove the isotropic part, we are still left with the symmetric. So we can infer from this that dij is also symmetric in ij. Hence we can interchange j and I in aijkl and receive the same expression. We get this expression. Now let's call this 1 and 2. Equating 1 and 2, we get mu minus mu dash times delta ik times delta jl minus delta il delta jk. This equals to 0. And this term may or may not be 0, which implies mu has to be equal to mu dash. The new expression for aijkl using this relation becomes aijkl equals to mu times delta ik delta jl plus delta il times delta jk plus mu double dash delta ij delta kl, where mu is the coefficient of viscosity and mu double prime is the second coefficient of viscosity. Now we can write dij in the following form, and plugging in the values we can expand it in this final form. Now we can easily recognize this first part as the symmetric part of the deformation tensor, and this as the divergence. Now let's define Eij as half of del ui by del xj plus del uj by del xi. So from this we can get ekk as del uk by del xk, and corresponding to this we can write dij as 2 mu times Eij plus mu double dash times delta ij times ekk. From the deviatoric part of the stress tensor we have dii equals to 0. Now plugging this in 3 we get dii equals to 0, therefore 2 mu ei plus mu double dash delta ij times ekk equals to 0, or mu double dash equals to minus 2 by 3 mu. Now using this value, this relation, we get this final expression for dij as 2 mu times Eij minus 1 by 3 times delta ij times ekk. This is the final expression for dij. So we have derived the expression for the stress tensor in terms of the velocity gradient by assuming that the fluid is isotropic. We next move on to substituting this expression into the equations of motion to obtain the Navier-Stokes equation. Based on the Cauchy stress construction, the fact that the stress tensor in a fluid element at rest is isotropic and that the stress tensor is symmetric, we had derived this initial equation of motion. This equation of motion, we need to plug in this final result into the equation of motion to derive the final Navier-Stokes equation. Now we know for a moving fluid element, sigma ij equals to minus p times delta ij plus d of ij. Using the value of dij that we have just derived, we get minus p times delta ij plus 2 mu times Eij minus 1/3 of delta ij times ekk. Now using this in the equation of motion that we derived earlier, so this was the equation of motion that we had derived. The equation of motion is rho times material derivative of the ith component of the u velocity or the ui velocity component equals to rho times the body forces in the I direction plus the surface forces sigma ij by del xj. Substituting the values, we get this equation, and finally we get this expression, that is rho times material derivative of ui by dt equals to rho times Fi minus del P by del Xi. Del Fi minus del P by del Xi plus del by del Xi inside this sigma ij term times Eij minus 1/3 of delta ij times Ekk and here this is the general form of the Navier-Stokes equation. Now finally, we simplify this generalized form of the Navier-Stokes equation for an incompressible fluid. Assuming the coefficient of viscosity mu constant, we have rho of dui by dt equals to rho of Fi minus dou P by dou Xi plus del uj by del Xi minus this term. Next, simplifying, we get rho of dui by dt equals to rho of Fi minus dou P by dou Xi plus mu times dou 2. The 2 here gets cancelled. Dou 2 ui by dou Xi dou Xj plus 1 by 3 dou 2 uj by dou Xi dou Xj. Next, assuming that our fluid to be incompressible, we have rho dui by dt equals to rho Fi minus dou P by dou Xi plus mu dou 2 ui by dou Xj dou Xj. This is dou Xj dou Xj dou Xi dou Xj. This is dou Xi. So yeah, this is the final expression, and we can finally represent this vector notation in this following form, that is rho du by dt equals to rho times F minus gradient of P plus mu times grad square U, which is the final Navier-Stokes equation for an incompressible fluid. So we started off with the Cauchy construction, stress tensor. From the Cauchy construction, this is the part A. So we derived the stress tensor. Then we proved that the stress tensor is symmetric, part B. Then in part C, we proved that the stress tensor is isotropic for a fluid at rest. And then from these derivations, we arrived at the equation of motion for this fluid element in the control volume. And next, we then moved on to the obtaining the stress tensor in terms of the velocity gradient by assuming that the fluid is isotropic. So this was the expression that we got finally, and then the generalized Navier-Stokes equation, and finally making certain assumptions, we simplified it for an incompressible flow, and we obtained the Navier-Stokes equation for an incompressible fluid. Thank you.